what we did at the previous lecture as a motivation of what we are going to do now. So remember that we considered the algebra of all polynomials in d variables for a fixed d, which is the dimension of the space, and we consider a state on this algebra which is equivalent to the polynomial assignment of a probability measure, and then we associated to this, algebra of polynomials are in the n indeterminates. I will use the notation d equal the set 1d, and the indeterminates is convenient to look at them as functions on the dual of Rd, identified with Rd itself in finite dimension, because in infinite dimension this notation will give you suggestion. Typically by the Bochner-Midlos theorem, the support of a measure is in the dual. And with values, with real values, so J belongs to D. So this is a vector valued random variable. Then we associated to this state the filtration of projections onto the increasing filtration of all polynomials of degree less or equal n. And then we defined the basic object, which is the gradation, the projection on the gradation, which is by definition the with the convention that is by definition equal to 0. With this definition, we define the Pn, the range of the nth projection, to be defined, this is called the nth orthogonal polynomial space associated to this. Remember that this is equivalent to give a scalar product on which makes P a pre-Hilbert space with the fundamental property that all the coordinate functions are symmetric, are self-adjoint. This is the coordinate. Then we obtained the three-diagonal Jacobi relation, which is this. The three-diagonal means this increases, this is preserves, and this decreases. And this suggested us to introduce the notation in analogy with quantum mechanics, A plus Jn, A0, Jn for the preservator, and A minus Jn for the annihilator. Summing over n, we obtained the quantum decomposition of xj, which is the sum over all an will be denoted simply aj plus a0j plus a minus j. The important point is that these objects satisfy the relations and the A0J are self-adjoint. Important is that this relation when you read it into the gradation, looks like that if I take the adjoint of J restricted to n minus 1, this gives A minus J restricted to n. Why this is important? Because when we use this decomposition restricted to n, I will use now this notation. This is by definition. Then you obtain, you see, that A daga is uniquely determined by this sum, but the last element is the adjoint of A minus 1. So the last element gives that A daga Jn is xj restricted to n minus A0 j restricted to n minus A plus Jn minus 1 adjoint. This suggested us the induction relation to reconstruct inductively a quantum decomposition of xj. So, given the state, we obtain the quantum decomposition and its inductive form, which is like this. And conversely, we reconstructed, given by inductively, given the sequence A0n, the A0n, the A daga plus, obtaining the A daga plus adjoint as a corollary. What we introduce in each step? What is the new element that we introduce each step we described the last time? In each step we need two things: the A0 preservator and the scalar product on the n plus 1 space. So at each step, starting from 0, which is canonical because it's one-dimensional. Now, in conclusion, what we found? We found that an orthogonal decomposition of P, given the state or the scalar product equivalently, all our scalar product from now on will be such that the xj are symmetric. So all scalar product will come from a state. This is equivalent to the pair Pn for each n and the family, let us say, of creators. This is for each j. Well, maybe it's convenient to say that now I have given this for each j in the index set D. Since remember that xj means xej, where E is the canonical basis of C power D. So once we have the canonical basis, instead of speaking of A daga J, we can speak of the map which to a vector in CD associates A daga V, which is by definition sum Vj A daga J. And J belongs to D. notice that this map is a complex linear, so the adjoint will be real linear, okay? And similarly for A0, which will be complex linear. So this A, this A daga will be a map from the CD space into the linear adjointable operators of P for the given scalar product. Now, it happens that this structure had been studied many years before in a much more general context, and this is what we discuss today, the context of interacting Fock spaces. At the end of the lecture, if I have time, but I am afraid I will not, but if you want, I can tell you the story of how these interacting Fock spaces arose, which is interesting because it shows that sometimes working on concrete problems, you come into some very basic and fundamental structure which arise naturally from very complicated structure. So what is an interacting Fock space? First of all, I fix notation, but you already are familiar with this notation. I call LA of H for any pre-Hilbert space the adjointable operators. So those operators which have an adjoint in the standard sense of Hilbert space. Now, definition. What is a vector space? What is an interacting Fock space? Interacting Fock space is that is given by two objects, a sequence of pre-Hilbert spaces and an A star. What is the sequence of Hilbert spaces? The properties are, first, H0 is one-dimensional with the standards, so it is generated by a single vector, phi0. From now on, it will be called phi0. With the scalar product, which is the Euclidean scalar product in the phi0 basis. So phi0 is norm 1 by definition. Now, what is the fundamental property of this pair, the pair defining the interacting Fock space? Fundamental property is, having a sequence of pre-Hilbert space, there is a unique way to define their vector space sum, to induce a pre-Hilbert space in the vector space sum by prescribing that this sum becomes an orthogonal Hilbert space sum, and the restriction of this scalar product on each factor gives the nth scalar product. So these are equivalent. This is obvious. Now, the fundamental property is this, that A daga, so I am defining, given a vector space V, which, remember, in our concrete case, the vector space is V is C to the power D, okay? For orthogonal polynomial, it will be C to the power D. But here, it can be anything, also infinite dimensional. So given a vector space V, we have this pair, and the fundamental property is that A daga is a linear map, complex linear map. When I say vector space, I always mean complex. Otherwise, I will specify. So this is a linear, so complex linear map from V to the adjointable operator of I remember I is the orthogonal sum, adjointable with respect to this scalar product. The fundamental property is this one, that it's a very simple exercise I suggest you to do, that this map is the left-hand side is a vector space. And this is identical to, so we require in some sense minimality, that Hn plus 1 is entirely generated by Hn by creation operators. So we eliminate all what is not essential to the, so this is a minimality condition, okay? Now, the operators A, daga, F are called creators in the interacting Fock space, and their adjoint, which exists by definition, remember, because by hypothesis, I am going A daga F is adjointable. This will be important in orthogonal polynomials, okay? And if n is equal to 0, Hn is called the vacuum space, and the corresponding vector generating Hn, H0, is called the vacuum vector. Remember, by definition, when I have a linear map, the A daga are linear map of a pre-Hilbert space into pre-Hilbert space. By definition, this means that the zero norm vector are mapped into the zero norm vector, otherwise the map is ill-defined. It's well defined as a map of vector space, but ill-defined as a map of pre-Hilbert space. Why is called interacting Fock space? Well, this is a delicate point. For some time I thought there is the Fock condition, which is equivalent to this is equivalent to this, is implied. However, it is implied by the other condition. However, this is not completely true, you see, because our filtration is one-sided. There are concrete examples in quantum mechanics of two-sided filtration. Filtration, well, as a particle filtration is still in some sense one-sided, but there is the simplest example is so-called finite temperature or equilibrium or Gibbs state at a given inverse temperature. There is a canonical construction to obtain this state, and here the number operator has a spectrum Z, not N. Okay? So the adjoint of A daga 0 can be A daga minus 1. Okay? In these representations. But, so, to require that, in our case, the filtration is one side. So, if we want to keep this condition, that A daga n applied to a vector xi in the space n, applied to a eta n plus 1 equal xi n a minus n eta n plus, well, I would say this is not so good. You see, because our filtration is one-sided, if I begin n with 0, here will be 1. But if I want to extend to the 0, I have only one possibility which is coherent with this prescription. And I write this prescription is in this way. See, but if n is equal to 0, xi minus 1 is not in our filtration, the E minus 1 space. So I have to define, in some sense, what is -1. And if I define the space -1 to be 0, then this will be coherent for all n. So this will be n-1, this will be n-1, and this will be n. And then I can write that it is for all n in n. In this sense, there is a unique possibility to do, because the filtration is one-sided. Okay, now, this is an important point on which our talk will be mainly an exploitation of this property. Why? Because what we want to do is this. We arrived to this. However, this Pn is very strongly dependent, the structure of Pn is very strongly dependent on phi, because it's the orthogonal nth orthogonal polynomial of phi, the orthogonal polynomial of degree n. So why are we introducing interacting Fock space? Because we are looking for a universal model, which will go for all phi, and will allow us to work independently of phi, to use this model independently of phi. That is our goal. In order to do that, we will bridge our concrete space. All these spaces are very concrete, but we will embed into a tensor algebra. In particular, in this case, we will have an homomorphism of the tensor algebra over CD onto this space, or the direct sum, the orthogonal sum of these spaces. Okay, this is what our universal model will be. However, since the xj are commutative, our universal model will not be the tensor algebra, but the symmetric tensor algebra. So the free commutative algebra generated by CD. The first step to construct is to go from, is to exploit. If you remember, one of the basic axioms of interacting Fock space was that the linear span of these vectors, remember, small v is in the space V, and small hn is in the space Hn. So the linear span of this is all of Hn plus 1. Okay? So we have the homomorphism at one step. So this is a trivial homomorphism at algebraic level, pay attention. Because at the moment we have no scalar product on this space, only on this space. So it is a trivial at the linear space level, because it's simply the universal property of the tensor product. Now, again, let us iterate and use the associativity of the tensor product. If you iterate this map, you will see that Hn will be the linear span of these objects. So this is an n-linear map, and therefore you have a linear map. Again, universality of tensor product into Hn. So all this, this is true for any interacting Fock space, not only for polynomials. For polynomial, we have to specify. So for any interacting Fock space, we have this linear homomorphism. And now we want to work a little to obtain a pre-Hilbert space homomorphism and to classify constructively how to build. So you will see some very similar properties. In some sense, interacting Fock space are a kind of non-commutative generalization of the orthogonal polynomials. Okay? So, an example. let me give you an example, very famous example of interacting Fock space. This example is in some sense universal, because our goal is to prove that any example, any interacting Fock space is an homomorphic image of this example. And this is called the full Fock space. Full Fock space is a Fock space which is, was used naturally in free probability as a model, as a kind of a GNS representation of the kind of states that appear in the free central limit theorem. And so, in quantum probability, full Fock space essentially was introduced in the context of free probability. And so, you have that if H is now, before we called it V, but now we are calling it H because it is a pre-Hilbert space, so it is a pre-scalar product. So I can canonically consider the tensor product, the tensor scalar product of order n, which is simply the product of the scalar product. It's a very simple exercise. This is essentially a corollary of Schur lemma. I don't know if you are familiar with Schur lemma. You know what it is. Everybody knows. You know. The Schur lemma says, if I have two positive definite matrices, Aij and Bij, their component-wise product, which means the matrix Cij equal by definition Aij times Bij, is also positive definite. This is an extremely important lemma for many theories, not only for probability theory is very important. Okay, and a corollary of Schur lemma is that since the scalar product is an example of positive definite kernel, positive definite matrix, you see the coefficients here are F and G. The product, this is the pointwise product of n positive definite, so it is positive definite. Okay? Remember, positive definite for me means greater or equal than 0. It can be 0 somewhere. You have to quotient to eliminate the zeros. Then, what is the creator in the full Fock space? Creator is simply the left multiplication in the tensor algebra. You have a natural structure of tensor algebra. It is a graded algebra. And creator is left multiplication. And we use the identification because the tensor power 1 of H, when n is equal 1, H tensor 1 is identified with H, and therefore we identify this with F. Okay? This is a very important example. Now, you have the creator. You have the scalar product, and you define the annihilator. And you now not define, you compute the annihilator. This is a simple exercise. If you take this operator and compute the adjoint of this operator, left tensor multiplication by F, the adjoint you compute with respect to this tensor product, you see that it is equal to this. Notice that it is different from the usual bosonic annihilator. Because it fills only the last one, not all. In the boson case, you have the sum F scalar Fj for all Fj. Okay. And now I want to say, you you say, let me recall and keep here the definition of interacting Fock space. So we have said that an interacting Fock space is a pair Hn with its own scalar product for each n. And A daga, and this is an interacting Fock space on a vector space V, and A daga is a map from V to the linear adjointable operator on the orthogonal sum of Hn. And we already defined that this orthogonal sum, there is a unique sum which is orthogonal and uniquely extends the scalar product. So we have this. Now, you may ask, the fundamental requirement is that this operator is adjointable. How this restricts the scalar product, the sequence of scalar products? This implies a constraint on the sequence. What is this constraint? Let me first explain intuitively, and then I show you formally. So, what is our point? We want that this operator is, we know that A daga, the operator A daga V, for each V in the vector space capital V, we know that AV is an operator of degree 1 in the orthogonal gradation. So it will map the space n into the space n plus 1. So this means that if I take a daga V applied to some vector n, I obtain something in Hn plus 1. Well, let me say U and V. So I take now U and V in capital V and Hn, H prime n in Hn. Therefore, if I have this scalar product, this will be a scalar product in the n plus 1 space. You see? But I want that each AU is an adjoint, the annihilator. So this will be Hn A minus U A V H prime V H prime n. I put n to remember that it is in this space. Not, but now the scalar product is in Hn. Okay. So this suggests you what is the constraint. The constraint is this: define the kernel for each n. Define the kernel. Kernel means omega n plus 1 is, kernel means a map from the set theoretical product into now the kernel where it will be valued. Look, this, sorry, this I forgot to put plus. Look, this is very important. A maps this into this. Therefore, the adjoint A minus for any U will map Hn plus 1 into Hn. This means that this operator is so-called homogeneous for the gradation. It maps Hn into Hn. So this is a linear operator, and is adjointable because it's a product of two adjointable operators. So it's a linear. a jointable operator in Hn with the scalar product n. Okay? This is our definition. So we define this in the scalar and scalar product. Now, there is the very well-known theory of positive definite functions, which is fundamental in probability theory, in group theory, in harmonic analysis, in a lot of discipline of mathematics. And now you see that we are naturally led, when we study interacting Fock space, to an operator generalization of this theory. Namely, our positive definite map has not values in C, but it has values into a star algebra, which is the star algebra of adjointable operators on a pre-Hilbert space. What is the fundamental property of positive definite kernel? You deduce from this property, okay? Because you know that the left-hand side should give you a scalar product. The scalar products are such that are positive definite kernels. So this is but it's very important that this is a positive definite kernel considered on the pair of variables. So let me be more explicit. I know that 0 is less or equal than the norm of sum of, let me say, A daga V H V, where V belongs to a finite subset of capital V, okay? Square. This object is equal to the sum of UV of A daga U H U A daga V H V, and by our definition of omega, the omega n plus 1, in fact I call omega tilde, for some reasons I keep omega tilde. So this is equal sum U and V. So now this is in the n plus 1, because this is n plus 1 norm. But this is in n, because we have HU, then omega tilde n plus 1 UV of HV, but now we are in the n space, okay? So we require this to be true for each finite subset of V, and for each map H from F to Hn, Hilbert space, okay? Since this map is arbitrary, what does it mean? Wait a moment. Here I am summing over both, because also this can vary. No, because this is the index. Okay, this was correct. Because, you see, this is a map. Okay, but the map is arbitrary. It means this can be completely arbitrary. Okay? In particular, I can take them constant. So it means, but the important point is that this is well, you can, if you have a minimum of experience with operator algebra, you can say that this is equivalent to say that for every map A is like an let me call another map. Let me call it T. Let me call it X. From F to the linear adjointable operators. Linear adjointable operators. Hn with scalar product n. This is a positive operator. The proof is trivial, because you can take, for example, this is an arbitrary vector. I can always write it like an operator xu times a fixed vector, say h. Okay? And here the same. I can write xv times h. I can always find an operator which has this property. Of course, well, a minimum, I have a minimality condition here, but I can always find. And so this has to be positive, but this is in the operator sense, and precisely in the sense of this algebra. Okay? So this is our motivation for introducing an operator-valued positive definite kernel. We generalize usual positive definite function. For C-star algebra, this was done in such operator-valued kernels were studied in connection with completely positive maps. For star algebras, we have a paper with Skyde, where we defined the theory carries over rather naturally for star algebras, provided that star algebra is a faithful representation. That is, the states separate the positive functionals separate the points of the star algebra. This is not true for every star algebra. There are some pathological star algebras without this property, so we want to exclude them. Okay? So this is the abstract definition. The abstract definition is this. If I have a set and the B is a star algebra, I define a map from S, the set S times S to be a B-valued positive definite kernel if this is positive in the sense of star algebra. Okay? This is a positive operator in the sense of star algebra for any, just, I don't repeat because I already said these notations, okay? And of course, if I have I gave this definition for a set, but of course, I can extend it to any set will generate a free vector space, so I have a linear map on this vector space. Conversely, if I have a vector space, I will have a Hamel basis. Is a Zorn lemma, a consequence of Zorn lemma that every vector space has a Hamel basis, and therefore I will possibly with infinite cardinality, and therefore essentially linear positive definite kernel and positive definite kernel on sets are essentially the same thing. Okay, this is the remark that I have written here. And so now, so I use this motivation. Every interacting Fock space defines a positive definite kernel. And you see, this is the relation which is between the scalar product. Because you see, we want the fact that it is adjoint implies that I can reconstruct the n plus 1 scalar product by the n, and this positive Gas-Finis kernel represents the additional information that I need. If you remember our construction with orthogonal polynomials, we were doing a particular case of this. Okay? Now, you may ask, can I choose arbitrarily the positive definite kernel, omega tilde, or not? You see that there is a natural, necessary condition. What is this necessary condition? So this was just for motivation of the definition, so we can erase. There is a natural necessary condition. You see, the point is, if we want this equality to hold, now suppose that I want to use in the direct formulation, I started for interacting Fock space, and I define the kernel. Suppose I want to do the opposite step. I start with the kernel, and I want to define something. Essentially, I want to define this scalar product, the n plus 1 scalar product. What is the constraint? Okay, the constraint comes from the fact that I have a map A-daga. Remember, that is why I recalled you. In the orthogonal polynomial, A-daga is uniquely defined. Once I have the preceding object inductively constructed, A-daga is uniquely defined. So it's not free, not arbitrary. So I have a constraint because if this A-daga is given, and I have that the sum of A-daga V, HV for a finite set F is equal to 0, remember, at this level, I have no scalar product of n plus 1. But I have my Hilbert space condition, my interacting Fock space condition, that A-daga of the vector space V applied to Hn is equal to Hn plus 1. And this is a vector space condition that I have. Okay? So if A-daga is given, I have a constraint because some linear combination can be 0. And therefore, what will be this? This linear combination will be 0. It means that this must be 0. So, if this is 0, it means that in the hypothetical scalar product that I want to define, however I choose AU and HN, the scalar product with a 0 vector must be 0. Obviously. And so this is this. If I want to define, but I am now defining it through the kernel. So what is this expression? This expression is, by definition, equal to Hn omega tilde n plus 1 u v h, the sum over V in F HV for the scalar product n. This must be 0. But this must be 0 for every U and every Hn. Okay? What does it mean that is 0? This is an element of Hn. I'm now in the n space. So it means that we are in a pre-Hilbert space. This must have norm 0. Because norm 0 elements are orthogonal to everything. Okay? So this is a necessary condition. If this condition is satisfied, I can define the scalar product. So this is the important point, important message. You see, it seems very vague, this structure. I just require that the creator is defined and as an adjoint. But you see that it is this is rather strong conditions, okay? You will see that in the orthogonal polynomial case, this condition fortunately will not come. And we will have in full analogy with the Favart lemma in one dimension, that this positive definite kernel will be the analog of the omega n positive in Favart lemma. And we will see that this cannot happen because of properties of the monic basis. Okay? So now let us go to the goal of today. We want the universal model. So the first step to define the universal model essentially means an iteration of the fact that this map is bilinear in V and H. So being bilinear in V and H, I have, by universal property of tensor product, a linear space homomorphism here. And I want now to lift to a pre-Hilbert space homomorphism. Okay? And so we do it with the following lemma. So now I have this, which is a pre-Hilbert space, and this, which is a vector space. I want to define the analog of the n plus 1 scalar product. So I want to lift the scalar product from here to the scalar. This is very simple because let me call T n plus 1 this map. Now, since I have a scalar product here, of course I can lift it here. Just I define V tensor H, U tensor Hn.
You have it in equation 12.
Huh?
No. Equation 12.
Ah, yes. No. Here, I am already speaking of a different thing. Because this is omega tensor, not omega tilde. Here, in this lemma, I want to show that all possible, also on this tensor product, all possible tensor product come, and for this I will use finite dimensionality. Here is more general. I don't use finite dimensionality, but I speak in general. I say I have this homomorphism, and I have this map into this space, so I can define U tensor Hn, V tensor Hn plus 1. Now, I am now defining in this space, which is not H a priori Hn plus 1. I want a universal model for it. So I define this scalar product as the scalar product of their images. And this is now in the space Hn, which I have, because it's in my assumption, okay? So this is just, we know that it is A, because the map, by definition, this map goes into this. So this is simply A daga U Hn, A daga V H prime, n into n. Okay? And we know that this is equal omega Hn omega tilde n plus 1 uv omega H prime n in this scalar product. I want to prove now that if I consider any scalar product on this space, I will have a kernel, but now this kernel again will be on a kernel on Hn. What is the point? Why here I have the adjoint. But if I want to prove that every scalar product on this tensor product has this form, I can use two things. Either that Hn is finite dimensional, or that Hn is a Hilbert space. Because if I have a Hilbert space, any continuous linear functional will induce me an element of the Hilbert space, because I identify the Hilbert space with its own dual. Okay? So I do the assumption in the finite dimensional case without assuming Hilbert space, because we will apply, our interest is to apply to this framework, and in this framework the space is CD, and Hn have dimension less or equal than Dn for Dn that we computed in the previous lecture. Okay? And so what we have is this. Any scalar product induces a kernel, but not a general kernel, and it must have the analog of this property here. Conversely, if I have a kernel that satisfies the compatibility condition, I will have a scalar product on this tensor product. Okay? So I leave the proof because it's very similar to the previous one. The argument we already illustrated here. And so now we can answer the question in general. So we have the one-to-one correspondence between n level in n plus 1 level interacting Fock space and positive definite kernels. And now you iterate. So you understand that each step you go, you see, it's very interesting. I don't know. This is a very interesting open problem in operator algebras. The problem is the following. roughly speaking, can I reduce, can I decompose my kernel? I know that that my kernel, if it comes from an interacting Fock space, it is the product of two operators. But these operators have a range in higher dimensional space. Because the range Eidaga V maps H n in Hn plus 1 and A minus in Hn. So I change dimension. Can I roughly speaking have a square root of this kernel? This would be the analog of rank 1 operators in or rank 1 matrices. So can I, intuitively, in my opinion, it's clear that not every kernel should be of this form, should have a square root. You see, inside the space. However, there is an abstract construction originally due to Kolmogorov. Well, he didn't do for operator kernel, but you can easily extend to operator kernels. And you can have a kind of decomposition like this, with the only point that is this space is a multiplicity space, more general, more abstract. You know that it exists, but it's more abstract, okay? So, in some sense, the message is this. If every positive definite kernel will be of this form, for some different space, Hn plus 1. But I don't know if omega, let me say, this is omega n plus 1, so this is n plus 1, is a positive definite kernel. This belongs to the adjointable operators of Hn with this scalar product. And the problem is, can I find some B such that BU is a linear operator, adjointable but on Hn, not from Hn to Hn plus 1, from Hn. Why I was looking at this problem? Because I was hoping that if I can find such a decomposition, this would give me an analog of the so-called symmetric Jacobi relation, which is this one. And I can write this relation all inside a single Hilbert space in the philosophy of the universal model. So, you see, what is the point? Now we have discussed the general interacting Fock space, in which, well, in fact, we did not finish, but now you can imagine very easily how to continue this, because I did just the first step, to pass from this to this. Once I have the first step, I can iterate and so the first step is this. which maps this into hn plus 1. Then I will have another which will map this, use associativity of tensor product, into this. See, when I arrive at the end and this becomes 0, this is one-dimensional. And so the last step, what will be? Simply the tensor product of V. And I find a map of this into, well, this, say, n plus 1. I will find a map here. And my scalar product will be here. So you understand, a universal model for interacting Fock space general is the tensor algebra over V with a scalar product. And this scalar product is given by the lemma that we have shown. That is, at each step it is lifted with a kernel, and you have the compatibility condition. Now, if we want to apply our theory to orthogonal polynomial, we have that this kernel comes from the identification of Vn tensor V1 goes into A daga V1. You see, this is, I'm iterating this step, Vn, A daga V1 applied to the vacuum vector. Huh? But we have proved, you remember, very fundamental property of interacting, of orthogonal, they commute. So we will have the further factorization into the symmetric tensor product. If we have an orthogonal polynomial. This is a special property, okay? And then the last step will be this. In the orthogonal polynomial, see, in the abstract interacting Fock space, this A0 doesn't play any role. But in orthogonal polynomial, A0 plays a role because A daga is defining using A0. Okay? But we know that A daga must have this form. And so we now have our general model. So in some sense, you understand why, the reason why Fock space as a symmetric tensor product came out. It came out because it comes in general for all orthogonal polynomials. It must be so. The universal model is that. It's not Fock space, but it is interacting Fock space. When you take now you have one-to-one correspondence. You see? And you have the analog of the theorem that we had with Bozzaico in '98 for one-dimensional case. Okay? The last part I ran a little bit. I outlined the idea. But if somebody of you wants more detail, please come and I will also give you the lectures. Okay? So for today is good. So we decided with Professor Krishna that the future lectures will, instead of continuing the overview of quantum probability, that there is the risk to say a lot of information on different topics and you lose track of it, we will go a little bit deeper into the direction of the multiplicity of quantum central limit theorem. So you will understand this topic more deeply, and you will see how the different notion of independence play a role, and how, this will be the most interesting thing, how to each notion of independence, it will be associated a corresponding notion of Gaussian state. There will be many, many, many notions which generalize classical Gaussianity. Okay?